Transportation Seminar at Florida State University. My name is Lemon Wang. I'm one of the fellows along with Dr. Miguel for the seminar. And for today, we're pleased to have Brian Gregor with us. Brian is currently a consultant for Oregon Systems Analytics. And after he retired from Oregon DOT, he's also the creator and developer of Reset suite of models that's used adopted by Federal Highway Administration and a number of other agencies throughout these areas. For today, we'll present some of his newer work on fuzzy cognitive maps to model policy issues in the face of uncertainty and limit data. With that, I will give the floor to Brian.
Okay, thank you, Li Ming. So I'll give you a little of my... I'm a transplant to Oregon, came here in 1977 and went to the planning school down there at the University of Oregon and graduated. Was a local planner in Tillamook County, working on their acknowledged comprehensive plan for a number of years, and then moved to ODOT, where I did environmental impact statements and was an environmentalist planner out in a region office, and then moved into policy, and then decided I got maybe in a way frustrated by policy being formed without a lot of analysis, and so I moved into the analysis side and got into modeling and developed several models. I developed a land use model called Luster, and then developed more recently the Green Step model, and then spun off of that the RSPM, or Regional Strategic Planning Model. And then I retired from ODOT, and I've got my own little business that I keep working on this stuff. And the thing that I'll talk about here is an interest of mine that went back to the early 90s, fuzzy cognitive maps. And Bart Costco talked about it in his book, Fuzzy Thinking, that came out then, and it intrigued me, but I never had... it never came together to have an opportunity to start working on them. And then ODOT had a project that I had proposed while I was there to use that to look at these new transportation technologies and services to hopefully get an idea of how they might affect transportation. ODOT was interested in that as a way to help figure out where to put money in research. So I'll be talking about using these fuzzy cognitive maps, and more specifically a variant of that I developed for this project. So I'll go through some background on fuzzy cognitive maps and what they are and their usefulness for modeling issues where there's uncertainty. Talk about some of the mathematical formulations of them and how this, what I'm calling fuzzy system dynamics model, differs from the standard fuzzy cognitive maps. Show you some open source software I developed, and it's on GitHub, so you can download it and play with it. And then talk about the results of the research with ODOT and OSU on modeling potential effects of new technologies and services. So, as we know, we really, in a way, can't do business as usual planning anymore in transportation, because the future is going to be very different than the present, or could be in a number of ways. That for decades, increasing automobility was just a given, and we could count on it. but we have a number of new disruptive technologies and services, such as the autonomous vehicle and services like Uber, and they're aggressively pursuing the whole idea of having autonomous taxis out there, driving down the cost per mile of taking them, and perhaps making it possible for large percentages of people in urban areas to go without owning any cars. We also have EVs are inevitable, and other more fuel efficient vehicles, and it's when you've got you're funding your transportation system off of gas taxes, that makes the future funding bleak unless you pursue some other revenue sources. And then finally, we've got substantial environmental constraints, and in my view, the big one being global warming and climate change and the need to become a carbon-free economy. So the uncertainty is, in my view, very large of what could happen in the future. And I'm illustrating this with this set of charts that comes from some other research that I've been working on. So if you look at vehicle miles traveled, basically you could say that VMT is the product of the number of drivers and what the average miles driven by each driver. So then if we look at the miles per driver, which I think is the big question, you could say that's the product of per capita GDP and then the ratio of miles per driver to per capita GDP. And the first two graphs show the trends. This is national data, and they look pretty linear. In fact, the second graph, I was really amazed when I plotted it that you see this ratio of miles per driver to per capita GDP going down in almost a straight line. And so in a sense, the inverse of that would be a productivity measure. We're getting more and more product with less and less driving. And so you could fit some nice straight lines to those trends, but you could also fit exponential curves. And the last graph shows what happens if you have straight lines that are fitting or exponential curves. So if you have per capita GDP growing linearly and our efficiency growing linearly, that makes a parabola, and it's a downward facing parabola, and you'd say with that future, gee, we're going to have less VMT per driver. I mean, we don't need to build anything. On the other hand, if GDP per capita grows at an exponential rate, and this ratio of miles per driver to GDP is exponentially declining, which might be more realistic than a straight line decline, because that means that on percentage terms, the percentage reduction is greater and greater each year, whereas an exponentially declining means that the percentage reduction from year to year is constant. But you get a very different curve if they're both exponential, and you can see the wide difference. So, and with this, what might encourage more efficiency? Well, if we have fleets of shared autonomous vehicles, we don't own as many cars. Instead, we pay to use a car when we want it. That could increase our efficiency, increase it. On the other hand, if we have owned autonomous vehicles and it's no longer a burden to drive, in a sense, you're still spending time, but you can spend that time doing other things. The utility isn't as the negative utility isn't as negative. You'd go further, So, and that might be the other trend. So we have to be able to deal with this uncertainty in considering policy issues. So this is a diagram I made a number of years ago to explain modeling, but in my view, everybody is a modeler. You know, we all are modeling. Some people are better at it than others, but we have these mental models in our head. And any time you try to use some reasoning, you are modeling. And I believe that a lot of the differences we have and conflicts is we're each carrying our own mental models in our heads, right? And we're not explicit about it. And so we come to different conclusions. So one, here you see the one saying, well, highway expansion causes the sprawl, which causes travel. And then the other saying, well, sprawl is causing the travel, which is causing the highway expansion. And you know, they're both right, you know, and if they were explicit with their models and put it all together, it would be maybe then something that could be used to develop better policy. So we're very accustomed to using mental models to reason about things we're uncertain about. But we don't necessarily do it explicitly, and part of the problem is with our, you know, our brains, there's only so much we can keep track of, right? It's hard to keep track of a network of a whole bunch of connections and think through all the connections, especially if there are feedback loops and all of that. So, and that's one where computers come in. You know, computers can keep track of those things and work through all the feedback loops so you can reason with that. And in my experience in working with a number of modeling projects that involved different stakeholders, that if people could see that their view of the world was accounted for in the model, that using a model actually helped come to some consensus about issues. Now, I'll transition to talking about fuzzy cognitive maps. So fuzzy cognitive maps are part of an area of study that's often called soft computing methods, and that includes fuzzy logic and fuzzy cognitive maps and some other things like that you set up computation using often linguistic terms like a lot or a little, and then behind the scenes your program converts that into the mathematics that then is calculated. So fuzzy cognitive maps describe causal systems as these directed graphs. So a graph is like this. You've got different nodes in it, which are some concepts, and then you've got arrows connect between those nodes. Where's my pointer? Oh, there it is. You've got arrows between the nodes, and those arrows identify causal connections. So in this case, you've got wetlands and then fish. So wetlands are affecting fish. And in the way this author laid it out, it's got a positive effect. The signs identify, just like in a regression equation, signs identify the direction of the effect, and then the values identify the weight, the strength of that effect. So, and typically in fuzzy cognitive maps, the values and directions go from -1 to +1. They're kept within that range. So in this case, wetlands would have a high positive effect on fish. So, and these might be described in terms rather than the numbers, it might be in terms of very low, moderate, high, very high, and then that's translated into a comparable numerical value. And often with these fuzzy cognitive map models, they're developed by experts. So they're not developed through a process of statistical estimation. You don't have a data set and then estimate a model using various statistical means. They're more of a way to encode expert opinion about things and what are the concepts, what are the connections, and what are the directions and strengths. So in standard fuzzy cognitive maps, they've also been called neural networks with feedback because they are similar to neural networks. And so basically, what these do is I think of them, they're very much like, in a way, a regression equation if you put that into a network and had feedbacks, that the value of each node is related to the value of the nodes affecting it. So as the equation shows, if you have R being this receiving concept, and you have a couple causal concepts, C, then the value of R in the next step, because this iterates, is the sum of the value of each causal concept times the respective weight. And then that's put through a function that's called an activation function. And the purpose of this is that it keeps the results within a value of 0 to 1. So this all works. Every concept is within a value of 0 to 1. So 0 being nothing there and 1 being the maximum value it could have. So there's some issues with this approach. So the weights represent relationships between the states of the concepts, right? So it could be if the causal concept, say the weight 1 in that is 0.5, it really means that absent of all other effects, the receiving concept would be 50% of the value of the causal concept. Right, so it's relating the states of those rather than the changes in the states of those. And in a way, it seems to me that that approach is saying this model determines what the state of everything will be. So you could go, it should describe all of history and all of the future. And in my view, the future isn't necessarily going to be like history. The present is a result of any number of things that have gone on in the past, including just historical precedent. And so we should be modeling changes rather than modeling values of states. The second thing is the meaning of iteration in this is unclear. These will, if you have any cycles in the graph, and let me go back just to explain what I mean. So if you have any feedback loops, and let's see if I can find one here. Well, here you've got one between wetlands and lake pollution. So wetlands affect lake pollution, and lake pollution affects wetlands. So if you have any feedback loops or cycles in your graph, the thing will need to iterate until it either converges to a stable state, or they may oscillate between several states, or they may never converge. And this can be a problem with these fuzzy cognitive maps. And so the iteration isn't really necessarily time. You can think of it more of the first set of calculations are the first order effects. The second set of calculations are the second order effects, then the third order effects, and they keep going until you get very little change. And then this activation function, what does that mean? Is it just a clever way just to keep everything working? And it's not clear what that meaning of that is in the real world. So the fuzzy system dynamics model is different. I changed things with this approach so that the weights aren't the ratio of one concept to the other, but they're elasticities. Okay, so an elasticity is the change of the thing being caused as a ratio to the change of something affected. So, for example, if you say the elasticity of vehicle miles traveled with respect to density is 0.2, it means that if you double density and increase it by 100%, or I'll say minus 0.2, it means that the VMT will change by a minus 20%. It'll decline by 20%. Okay, so these weights are are change ratios rather than the ratios of the states. And so you calculate the sum differently. And maybe I won't go through the math there, but say if you have two things affecting two concepts affecting a third, and say if the one concept, the causal concept as a result of, or the receiving concept as a result of the causal is reduced to 80% of its value. And if it's the result of applying the second causal concept, it would be reduced by 90% of its value as a result of that. Well, you multiply those 0.8 times 0.9 to get the total effect. You don't say that if the one is reduced by 10% and then it's reduced by 20%, you don't add a 10% reduction and a 20% reduction to get a 30%. So I can answer questions about that later. I won't take up too much time doing that. So these weights are elasticities, but you still need to modify the effects of those, and because you can't expect elasticities to be constant over the full range of values of the causal concept and the receiving concept. So, for example, if you have 1% of bicyclists, or 1% of trips are by bicycle, and you double it, you have a doubling of that, it's going to have a small effect on the amount of auto travel, right? So if you have 50% of the trips are made by bicycle, and you're going to double it, then you're going to have a big effect, right? So the effect of a cause on the receiving concept will increase as the causal concept increases, but it reaches, and what I postulated for this model, it increases to some maximum.
And on the other hand, if you have something that is being affected, or a receiving concept, it's going to be very sensitive if there's not much of it, when it's small. But when you're getting towards, say, you can think of it in terms of market saturation. When it gets close to fully saturated, it's very hard to change it anymore. So what this lower graph shows is this sensitivity, which is multiplied by the weights. So the red is showing the causal sensitivity, which is very small, and then it grows to be 1, and the receiving, which actually the current form in the model is greater than 1 at very, very, very low levels, and then it comes down to 1 and then declines to 0. And this is, I'll point out later, this is something that more research is needed on this, to talk to research more the theoretical foundations of it. It works in the model, but I think it would be good to delve more into why does that make sense. And and what is, because these are elasticities, you don't apply elasticities to big jumps. My example of doubling a density is not the way to apply an elasticities. Elasticities are applied in small increments. And so the way the model works is that small increments are made to a causal variable, the one you want to study. Say you want to study increasing density, and then the model runs to, because again there are cycles, it has to iterate, and it runs till it closes, and then you increment again. And in that way, then this model can, in a sense, represent time, because you can represent time as what are the time steps for increasing density, and then see the effects as a result. And all the values then in this model are in the range of 0 to 100 to represent percents. So, as I was saying just a minute ago, all of the concepts of interest are incremented in small steps, and then with each increment, the model cycles to closure. And you can see, so in this top diagram, you're seeing the small steps in a causal variable, and then in each step, the model is cycling till it gets to equilibrium. So I'll quickly go through some steps and then show the software to apply these models. So first you define the concepts being modeled, and what you can just model everything in a range of 0 to 100, but it's set up so that you can talk about real-world units, like persons per square mile. And you set up the range. Here's the minimum value we'll consider for the range, and here's the maximum. And it's important to, I think, one of the values of this modeling is to get you to think carefully about what you're doing and define your terms carefully. So what do the causal concepts mean? How are they measured? And then you can group the concepts into related groups, and I'll show you that with the demonstration to better understand and also see portions, because these graphs can get very big, these cognitive maps, as I'll show you. You then specify the causal relations, and again, positive is is an increase and negative is decrease. You specify the relative magnitude and of the relationships, and then you start working with scenarios. Let me just make sure my phone is off so I don't interrupt my own talk. So I'll now show the software, and this is all open source. ODOT, when they fund something, they make the software open source, and it's on my GitHub page. Let's see, where is that? There it is. Okay. So basically you have tabs which work through the basic parts of building one of these models. You have a Build a Model tab, and that includes establishing your user information, selecting a model, editing concepts, editing relations, and saving the model. And then you create scenarios, and you select them and edit them. You run the model, and then finally you analyze the results of the model. And so with building a model, the user information, one reason I built it with this is so that you could keep track of who made a model and who did the edits and when, so that it's all documented. So I'll select a model, because if you run a model without editing, then you don't have to give the user information. And I'm going to do the simple fish model, and then I'll show you what. So you have concepts, and this is the same as I showed in the slide, and then it's important to, I think, document this. What's your meaning of everything? And so fish here is just the quantity of fish, percentage of maximum carrying capacity, and I made this up. So extent of wetlands and watershed is wetlands, and percentage of historical extent. So you define all these concepts, you establish your minimum and maximum values, and you can also put them in different groups. And then you can look at your relationships, and this is something I'll have to scroll. So since this is already built, all the relationships are there, and you can then add relationships. If I wanted to add let's see, maybe income. With more income, there's more pollution. So I'll say income and pollution, and it's positive. And how does income, or maybe it's income is less pollution, because it'd be demand for less, but I'll just say it's low. And then, I can't do that because I'm in run-only mode. Sorry. But you would do something like that, and it would add that in. And then you can have different scenarios. And You can either create something from scratch or copy a scenario or just choose one, edit an existing one. So here's an enforce one. And then you describe what is in that scenario, what you're changing. And in enforce one, what we're doing is increasing the enforcement level from like 25% of a maximum enforcement to 75. And again, you describe it. Enforcement of wetlands, fishing, and pollution laws is greatly limited. A tripling will greatly increase for enforcement, would still be below full level. And it's set up to with validation so that the scenario values are checked against what's allowed in the model, so that you know it will run. You won't get a runtime error when you run that model. And then you run the model, and you can list all the scenarios that can be run, and then below it says what scenarios haven't been validated. And here we have my test scenario called bad scenario, and it can't be validated until it's consistent. And then you choose which ones you want to run, and you run the model, and it says model is running. It's usually faster, but I think having all this stuff open slows it down. And then there's a simple thing to analyze the results. So we can take these two enforcement scenarios, and let's just check all of the outputs, and then you can compare the two enforcement scenarios. So that is, enforcement is ratcheted up in the scenario, and you can see enforcement with this line, as that's ratcheted up, you see big increases in fish and income and decline in pollution. And you see with the lower level enforcement the respective results of that. Now, the advantage of, again, this is in a way, it's a computer, it's an enhanced mental model, and it forces you to document it well. And I'll go back to show the model, just to illustrate or talk about how this can help in policy discussions. So, say in this scenario or this situation, people say, look, you can't, we're poor people, we need to fish, we need to build factories. If you're putting in this enforcement, it's going to drive down our income, right? If you regulate more, it'll drive down our income. And you say, okay, we have an arrow there. More enforcement lowers income. But on the other hand, you have other pathways. If enforcement enhances the wetlands, and if the wetlands increase the fish stocks, then there's more fish to catch. And if you have enforcement reducing pollution, and it becomes then more attractive for tourists to come in, who are attracted to the increased fishing, then that increases income. And so to really think through this policy, you can't, you need to think about how all of those things interact. And if someone says, well, gee, it's not low, this effect of enforcement on income, it's moderate or it's high, you just change the value and you run it again. Does it really, how much does that change the outcome of it? So I think I better go back to my presentation because I want to give you time for questions. So this model was built for really because ODOT was interested in having a better idea of how these new transportation technologies and services could affect travel and the operating characteristics of the highway system. So, so there are a number of things that are coming along that could affect travel behavior and operation. You've got your autonomous vehicles, as I mentioned before, and you've got the prospect that people will own these vehicles and the prospect that they'll be shared. You got connected vehicles, so if these vehicles are talking together, they can be in synchronized queues and increase capacity. You've got the intelligent infrastructure that relates to the connected vehicles and also to, say, intelligent routing of and dispatching of transportation services, the mobile technologies that tell travelers about what's available, and then you've got demand-responsive transportation service, such as automated taxis that might be automatically dispatched and controlled. And then on the lighter weight side, you've got, with lightweight batteries and motors, you've got lightweight electric vehicles, so electric bicycles, and which can open up the market for lower impact transportation. So the research was sponsored by the Oregon DOT, and Alex Bettinardi there is the project manager of this. And then there's a research team of myself and Haizhong Wang at OSU, and then Rachel Vogt, when she was a graduate student, worked on the early parts of this research. So this is by no means done, and I'll talk about follow-up. And so this is kind of my concept of things, what I did here is say there's really three types of autonomous vehicles. There's full autonomous vehicles that are owned by people. There are partially autonomous vehicles that are owned by people. So that would be like, lane guidance, keeping you in the lane, or automatic braking. And then there's shared autonomous vehicles that are fully autonomous, but you don't own them, you just use them. Those would be autonomous Ubers. And the cost has effects on these things. The amount of autonomous vehicles affect connected vehicles, and intelligent infrastructure affects that. Shared autonomous affect demand-responsive transit, which then also affects transit access, which affects fixed route transit. The lightweight electric vehicles also affect transit access. So, so there's a part of it that is the transportation technologies and services part. You've got travel outcomes, which I blew this up from the program, and so it got kind of blocky. But you've got it's quite complicated, as you can see, but you've got things like density, the proximity of destinations to each other, relative auto capacity, congestion, auto trip distance, auto trip cost, non-auto trip comfort, non-auto trip, so VMT, and a whole set of positive and negative linkages. And then finally, you have the connections between the technologies and services and the outcomes. So owned full autonomous vehicles, for example, here positively affect auto comfort. And auto comfort was in the other part of the model. That positively affects the amount of auto trips or the distance of auto trips. And then it also, the full autonomous affects auto trips because you could have, for example, say when I worked at ODOT downtown, I had to pay for parking. But if I had a fully autonomous vehicle, I could drive in, get dropped off in my car, just go back home and park for free, and then come back. So it basically doubles the number of commute trips I make. That's one of the prospects. So a number of connections there. And one of the things tested with this was to look at some basic travel behavior relationships and see how they line up with what the model does and what real world is. So I collected data on 50 or so metropolitan areas on a number of these variables included in the model. And it could only be a small set. And then tested a couple things like what if, starting with something that is sort of like Portland, what if we double density and go from where it starts and where it ends up? And how does that relate to the values you see among all the metropolitan areas? So this cloud of values, or the values in this case of density versus congestion. And as density goes up, congestion generally goes up. And in the test, when we increased density, congestion went up. Now this is a earlier version of the model, so I haven't tested it with the current version of the model. Here's density versus vehicle travel. As density goes down, vehicle travel goes down, and the model has it go down. Density versus speed. As density goes up, speed tends to go down, and the model goes down. And density versus auto ownership. As density goes up, ownership goes down, and the model is pushing it down. So it's going in the right direction. And then, so here you can see with the present modeling, in this case, the increasing capacity by 50% versus increasing density by 50%. So you can see that the density is the light blue, and if you increase capacity, as you'd expect, density goes down. If you increase capacity, then your VMT, your congestion is going down, your VMT is going up. And your non-auto trips are going down slightly. If you increase density, your congestion goes up, your density, of course, is going up, your auto trips are going down, and your non-auto trips are going up. So it's doing what you would expect it to do. And then here's a comparison of increasing capacity with decreasing autonomous vehicle cost. And so the capacity is just like you saw in the previous. If you reduce the the autonomous vehicle cost, congestion also goes down, and VMT is going up. But you'll see down at the bottom the number of demand-responsive transit trips is going up, too. And it's even more interesting with the model if you run it 100% autonomous, because what it does is in the early years, VMT is going up, and then it crests, and then it declines some. And what this model is doing is saying, well, the demand-responsive transit is really growing, and as demand-responsive transit goes up, then that's pulling VMT back down again. So in conclusion, I believe we need models for every planning domain. Even these domains that are squishy, that we don't have a lot of data, it can be helpful for people to think carefully about the chains of logic and use a computer model to work through that. And It's useful because it enforces consistency in reasoning, and I think helps form consensus. And I think this is a promising model approach for these policy matters involving uncertainty. And it's very easy to change, so you can, if people have different views on it, you just change an arrow and you change the value and you run it and see how much difference it makes. So as far as next steps go, ODOT's got an independent review underway. And they've engaged a consultant or consulting team to look at that futures model and evaluate it and other alternatives, and also evaluate the usability of the software. I hope, along with my co-authors, to get an article out that we can publish on this, and more other documentation is needed. And then there's more research needed, as I mentioned before, on this sensitivity function, the theoretical underpinnings of that. I think it'd be good to use fuzzy numbers for the weights rather than a weight of 0.5. You have a fuzzy function for that. And then I think it would be helpful to put together some guidance on setting weights. For example, if you know something is a direct relationship, like the relationship between fuel economy and fuel consumption, well, that's high. You have fuel economy, you'll have fuel consumption. But I think you can develop some guidance for how to go about establishing some of these relationships. And then finally, there's some contact information and acknowledgments. So I ran over in the presentation. I hope I don't constrain questions too much. Yeah.
Richard Henry. I had a question about the time aspect, since this model doesn't use time.
Right.
It's just the state of things as you would want them to be. I was wondering why that wasn't included. Was that just too difficult to model? Or just because it's not that important?
No, it's a matter of how to figure out how to do it. Okay. Yeah. And there's another interesting aspect to that is that the interactions may be on different time scales. So the effect of feedback on density you would expect to be on a slower time scale than some other things. And so the way I handled that is to think of that in the weights, so that if something was at a slower time scale, then if you think of everything on a constant time scale, then something that acts more slowly should be represented by a lower weight of effect. But good research. Future research.
Yeah, kind of another question. So you said the iteration process was kind of sort of made up for the time aspects. You iterated slowly.
Right.
Instead of doubling the density overnight, you double it slowly.
That's right. And so you might think about that as being, how long would it take to double density?
Yeah.
So then you're thinking, well, if it takes 50 years to double density and you're incrementing over 50 time steps, each time steps a year.
Yeah. So if somebody's making a policy decision based on this modeling, and but they can't get they say they want to increase bike traffic, but they also want to, the model they set up using this, they want to increase bike traffic to do one thing, but they also need to increase gasoline taxes for another reason. Mm-hmm. I'm not sure. It's just making stuff up.
I think this is more of I see it less as a predicting the future state, as saying, what do the different levers do, and are they acting, are there sort of consequences, like with the example of the fish, that someone might argue, you increase enforcement, it's going to tank our economy, it's going to hurt our economy. well, will it, given that there are a number of different pathways where enforcement affects things related to income? And so I think it's more of improving the policy discussion. I'm not sure how much I'd say that I'd use it to forecast a value.
So it's just demonstrates consequences, or like how all policy affects everything at once. So I guess it just shows like how things work.
Yeah.
Rather than
well,
how
people have a hard time understanding how systems work.
Okay.
And it would help with relative magnitude. So policy X could have a bigger effect, than policy Y, given the reinforcements and feedbacks. Yeah.
What other fields you're most excited to see this sort of software and these sorts of processes applied to outside of transportation, since it has such wide applicability, or seems like it could?
Yeah.
I think it could work in, like the example there of it basically like environmental regulation, or it might work there. It maybe in housing policy. Not sure what else. Yeah.
On one of the first maps you showed, one of the concepts had an arrow going to itself.
Right.
What is that?
So
that would be in how you could think of it as a herd effect. That people start buying something and then it gets buzz and other people buy it, So self-feedback. It feeds on itself. Yeah, Christy.
There's a bigger policy discussion in JAPA happening right now, looking at another meta-analysis of the built environment and travel behavior relationships.
Uh-huh.
And one of the questions it's bringing up is whether we can evaluate or think about these relationships based on elasticities. And I think specifically this started coming out when we started thinking about location disadvantaged populations and low-income populations, where a policy effect like increasing transit quality might have a negligible small effect at a regional level, but for that specific population, it's life-changing.
Right.
So I'm wondering, well, how, if you're thinking about this and you're thinking about for the region of Portland,
Right.
how do these levers play? How do you segment out specific populations that you might want to be careful of not, overlooking?
Yeah, I wondered about that because I was thinking also how much you use this to look at issues of income equality, and you'd have to segment out. I would think you could do it, but I haven't tried. I mean, it might get to be a very complex map because you basically would have to map out how things affect each of your groups and have different elasticities. And it is challenging with this to sum up, figure out how things sum up. So,
So I was curious, on some of the slides they showed, they did have values for the weights. And then on the website, I was wondering, could a user actually have numeric values for the weights, or is it just like high, medium, low?
I set
that up for high, medium, for just to make it simpler to think of a model, because you don't want to get into arguments, well, is it 0.5 or is it 0.55, and so it's just set up with the, categories, and that's where it'd be nice to have fuzzy numbers, because something that's medium, say, is over a distribution. Medium means a distribution. It might be centered on 0.5, but if you get away from 0.5, you're still somewhat medium.
So let's thank Brian again for the talk.